Hello everyone, my name is Junyoung Lee, and I am a student at INGIST Korea. The topic of my presentation is Evaluation of Test-Based Biofeedback and Warning for Improvement of Seated Balance on a Trunk Rehabilitation Robot. The presentation will be conducted in this sequence. In this work, we have developed and evaluated a transcutaneous electrical nerve stimulation-based balance biofeedback or QE system to serve as a substitute or adjunct to visual balance biofeedback during seated balance rehabilitation of people with visual weakness. The hypotheses evaluated in this work are that TENS-based balance biofeedback may be a viable alternative for visual balance biofeedback and may have better performance than vibrotactile biofeedback due to its better localization. Provision of warning before perturbation may improve balance recovery, and the use of a modality different from the one used for balance biofeedback may produce greater improvement. The seat of the trunk rehabilitation robot used here has load cells to measure the user's COP position and can perform pitch, roll, yaw, and heave movements. The roll and pitch movements correspond to ML and AP movements of the body. The seat can move either according to COP movement, called unstable mode, or according to a preset movement plan, called the perturbation mode. The user sits on the seat and places their feet on the seat-connected footrest. During unstable mode, a monitor is placed to provide visual feedback in the form of a display of 8 arrows. All arrows remain deactivated when the user's COP is inside the target region. When outside this zone, the user should move according to arrow indication to bring their COP back inside the target region. The vibrotactile and TENS feedback systems also operate in the same manner, except that the arrows are replaced by 8 vibrotactors or pairs of electrodes placed around the user's abdomen. The actuator locations for these systems are shown in the figure. The TENS feedback system controller takes command from the TRR operator software and generates control signals for the TENS devices. The electrode provides stimulation with a comfortable yet clearly perceivable intensity that produces a sensation of vibration at the electrode pair location. The vibrotactile feedback system works in the same manner as the TENS system. When a signal is to be delivered, the corresponding vibrotactor is turned out at full intensity. During perturbation mode, continuous feedback of the current COP position is provided in the form of a plot with the target region. For visual warning, arrows corresponding to the 8 perturbation directions are placed around the COP plot and activated as figure shows to give the warning. The vibrotactile and TENS feedback systems also operate in the same manner. During our trials, the participants tried to keep their COP inside the target region. No feedback and no warning conditions were also included in these trials. One perturbation in each of the 8 directions was included in each trial. The 8 trial conditions used in this study are listed here. 2 trials under each condition were carried out with a break of 1 minute between trials. All subjects wore an inertial sensor at the lower thoracic level to record their trunk accelerations. The COP data recorded by the TRR were used to calculate mean velocity displacement, distance from center, ML trajectory, and AP trajectory using the equations shown here. Linear accelerations of the lower strokes were extracted from the IMU data. The RMS values of these accelerations in the ML and AP directions were calculated using the equations shown here. The overall results under unstable seat mode show that the vibrotactile and TENS feedback modalities both may be viable alternatives for visual feedback. However, making a clear choice with the available data is not possible due to the lack of significant differences in outcome measures, which may be attributed to high variation in subject performances. Results under perturbation mode show that advanced learning in the form of a visual or tense signal significantly improved balance performance. This supports our hypothesis that seated balance recovery may benefit from the provision of information about the upcoming perturbation. The directional comparison results indicate that seated balance may be more sensitive to perturbations in the ML direction. They also show that balance recovery under ML-directed perturbations may be more sensitive to provision of augmented information. Overall, these results show that the visual and tense modalities may be feasible for perturbation learning, whereas vibrotactile stimulation-based learnings may not be as effective. The movement complexity results show that 2D perturbations generally caused greater trunk accelerations and elicited greater values of ML-directed outcome measures, showing that seated balance in this direction may be more sensitive to the complexity of perturbation. They also show that tense learning may be helpful in improving balance recovery through reduction in trunk accelerations and may have greater efficacy under more complex perturbation conditions. The results of this study leads us to conclude that provision of a warning before perturbation may improve seated balance recovery. Use of vibrotactile stimulation for the tested applications may have limited efficacy. Use of TENS to deliver balance biofeedback or warnings may be feasible for robotic seated balance training. However, since this study was done with healthy subjects, studies with patients are required to confirm these outcomes. Thank you for your listening.